Morning, everyone. I hope you guys have been able to look at the lectures from the last weeks and last 2 weeks. I've repeated something to you guys over and over again. What is that I've repeated? For a non-zero nuclear spin, there exist multiple states, which when suspended in a B naught end up being non-degenerate, and you end up applying a radio frequency wave to assist them, right? Before you end up even assessing them, let me move this one step away. This results in a bulk magnetization along the B naught, which can be interrogated with an RF pulse. This is where we are. And what all terms did we define? Let's try to draw some of them. For some, this might feel like a boring repetition, but I'm repeating something over and over again so that it gets ingrained in your thought process. I hope you guys are able to recollect how the M naught comes up, because you're talking about the spin states, which resolve themselves as a population excess, slight population excess, making NMR an insensitive technique proportional to gamma and B naught. So that was the message there. And at the same time, for the RF field, the most part of what we did last week was to understand and appreciate, depending upon the offset that is being present, there will be a tiny bit of magnetization that exists along the z-axis, which depends on the offset. So this is the B effective. Now, what all did we define here? We defined a tilt angle theta, where the tilt angle theta is given as the tan inverse of omega 1 over capital omega, where capital omega was defined as omega naught minus omega RF. This is under the condition that we ended up applying a B RF, that is of the form 2B1 cos omega RF t plus phi times I, which when you resolve it into two counter-rotating light and go to rotating frame, ends up being B1 in the rotating frame, BRF in the rotating frame becomes B1 cos phi I cap plus B1 sin phi j cap in the rotating frame. And the effective B field in the rotating frame would be given as BRF rotating plus delta B naught K cap. So this is where we were, correct? And we also said what is the magnitude of B effective is going to be B1, magnitude of B1 by sin theta. Is that correct? Yes? These were the different dependencies that we ended up deducing. And why did we take so much of pain to do this? Because if you understand what is B effective, then we can understand what is the evolution of magnetization in the rotating frame, which is going to be given by M cross of gamma B effective, where B effective is B plus omega over gamma. So the moment you understand how B effective looks, you'll be able to say how the magnetization changes, because it will end up processing about the effective B field. Okay? We wanted to understand the B effective so that once you have an M, you would be able to determine how the magnetization will end up behaving. The rate of change of different components is going to have different rates of relaxation, rate constants of relaxation. These were ad hoc defined by Bloch in order to define the evolution of magnetization as a function of time, basically relaxation. So these were the equations with which we left off in the last class. I would like to know why did we define two different relaxation rates? Can one of you please explain it to me? Why did we choose one as R1, the other as R2? Why can't we have a common relaxation rate R? Yes.
One's going to be the dephasing thing.
Which one is the dephasing thing?
The transverse rectified.
So R2 is going to be
For the dephasing part.
the loss of phase coherence. Basically, loss of phase coherence. Phase decoherence is what is R2. Okay, that is a mechanism in which R2 manifests. What is the name for R2?
Spin relaxation.
Very good. It's spin relaxation. So can somebody else tell me what is R1? Okay, spin lattice relaxation. Why do you have to give a different rate constants from transverse? As he said, transverse magnetization is due to phase coherence. The loss of phase coherence is what is characterized by R2. Now the question is, why can't you just use R2? Why do you have to use a different constant R1? Yeah, the reason why you get a Z magnetization is due to population difference. Since the mechanisms in which the transverse magnetization and the longitudinal magnetization are created, we have to have different rates for them to recover. Okay, so with that being said, let me continue to the next point. Can one of you tell me what did you get for mx of t once you ended up integrating? It's first order rate, right? The dA by dt is equal to k times a with a minus, of course. We generally have minus dA by dt equal to k times a for a first order rate kinetics, correct? Rate of disappearance of reactants is minus dA by dt is equal to k1 times a, where k1 is the first order rate constant. So for that, very good. Mx of 0, just a moment. Mx of 0 times t. That should be a t variable, right? dt is there. Okay. So I hope the people who ended up deriving got this. This is rather straightforward. Literally the same thing you're going to get for my of t, which is going to be my of naught times exp minus r2t. For people who are still confused on what is this mx of 0 and what is this my of 0, these are magnetizations. I'll write mi of 0, magnetization present along ith axis after application of pulse. Okay, if you end up applying a 90-degree pulse, let's take an example. We saw this in simulation as well. We'll see more of it as we go. Let's assume you end up applying a 90-degree pulse. Let me take, for the sake of it, along the y phase. We'll understand what is the phase as we go forward. What do we mean by y phase? Phi is set to 90 degrees. This will end up giving mx of 0 following application of pulses m naught, my of 0 as 0. All this means is that you ended up tilting the Z magnetization entirely along the x-axis. Why is it counterclockwise? We'll try to see as we go forward. Okay. Similarly, if you end up applying a 90-degree pulse along x where phi is 0, you will have mx of x equal to 0 and my of 0 is minus m naught. We'll see why that's a minus coming in. It's counterclockwise rotation. For people who would like to imagine this, you have 3 axes. I always use a right hand. Most of us end up writing with our right hand, and therefore it's easy to look at left hand. Everything changes there. So be super careful. Okay. Always look at your right hand. If the forefinger is the x-axis, middle finger is the y-axis, thumb finger is the z-axis, you end up having a counterclockwise rotation. I'm applying a pulse along the y-axis. It ends up tilting the z to x. Similarly, if I end up applying along the x-axis, it'll end up converting z to minus y. That's why the minus sign comes. We'll see why the minus, why is it counter-rotating, counterclockwise rotation as we go forward. Okay. So these are 2 important equations, which we will once again come back to as we go later on. Okay. Now, at the same time, we also have to understand what happens to mz of t. Can one of you tell me what is the answer that you got? Go slowly and louder, please. Like this? Is this correct? This appears correct to me. So for a similar example, let's try to understand what is mz of 0. Mz of 0 carries the same definition as of mi of 0, meaning that after the application of a pulse, when you're starting time 0, what is the magnitude along z? So when you end up applying a 90-degree pulse, that's going to go to 0. So let's write the same thing. I'm doing this explicitly. I'm not saying x or y axis. It does not matter for z along which axis you ended up applying. Yeah. Only for the transverse magnetization matters where it comes. Doesn't matter whether it's x or y. Mz of 0 will be 0 after a 90-degree pulse. Similarly, for a 180-degree pulse along any of the phase, what is going to be mz of 0? Yeah, makes sense. So this is very important. What you guys are able to realize here is that the moment it goes to 0, then you have m naught of 1 minus e power minus r1 times t. Okay. I'm going to draw a few set of plots that's going to help you guys understand how these functions look. So I'm just going to take mxy. These plots matter so that you understand how these end up behaving. How does it work out? You actually start at a certain mxy of 0. Then it just decays a first order rate, right? For chemists, you might want to say log of magnetization as a function of t would be linear, right? Once again, going back to first order, there the slope will be minus r2, right? Let's not do such things. This is good enough for us. Are you guys able to realize that the transverse magnetization decays as a function of time, right? These are very obvious. I'm repeatedly telling it so that you guys will be able to catch up at some point of time. Similarly, mz of t as a function of time, depending upon where you start. You could have different types of recovery that comes here. You could have a recovery if this is 0, then this is going to be somewhere at m naught. Of course, it will reach m naught only at infinity. I'm just drawing it for the sake of it. At the same time, if you ended up applying a 180-degree pulse, you will end up having a recovery that goes from minus m naught to something like this. The rate will still be the same. So initial rate will be much faster for 180, which makes sense, right? Because you will have m naught minus 2 m naught e power minus r1t if it's a 180-degree pulse. Correct? So the prefactor for the recovery will be faster initially for a 180-degree pulse than 90. But the rates are same. The rate constants are same. Okay? The instantaneous rate initially will be different. It will be slightly slower here than here. But the moment it reaches here, the rate here and here will be one and the same. These two will have almost a parallel difference. Make sense? Okay? So the important terms that one has to look for: transverse magnetization decays. Longitudinal magnetization recovers. These are the terms you should say. You should not say the longitudinal magnetization decays. There's no decay there. It only recovers if at all. Okay. Similarly, a transverse magnetization once created will only decay. That cannot develop. It can develop in some rephasing experiments, but let's not go there right now. Okay. So whenever you're talking about transverse magnetization, the relaxation will be termed as a decay. While you're talking about longitudinal relaxation, it will be called as longitudinal magnetization recovery. Make sense? Good. Now let's put some numbers into it. Let us say that you started here at 100%. Can you guys take the next 5 minutes? Or no, not 5 minutes. Can you guys please take the next 1 minute to tell me when will this magnetization go to 5% of its initial magnitude? Let me repeat the question. Initial magnetization, let's assume after a 90-degree pulse is applied, is m naught. When will it go to 0.05 times m naught? What is the time t? Right time t independence of R2. How long? T equal to? Louder? 3 by 3 by R2. Can I write it as 3 times T2? So what does this mean? For a magnetization that you have generated along the transverse plane, it takes 3 times T2 for it to decay to its 5%. Then you would ask, who chose this 5%? There is something called noise, which I'm not plotting here. Generally, if the noise gets there, you might not be able to see the 5% of magnetization. Now, I want you guys to repeat the same exercise. It's rather simple. You started with 0% of m naught along z after the pulse. I want you to tell me how long will it take to recover to 99% of m naught? The time. Same question. This is for longitudinal recovery. I want you to express t in terms of R1 or T1. Please tell me what it is.
4.6.
4.6 is it? Times T1. I thought it would be 5 T1. 4.6 times T1, right? Okay, maybe it's 99.5% I'm thinking. But overall, what you guys are able to realize, this T will be approximately equal to 5 times T1. These are very important numbers to have because we chose a few numbers to imagine this. We said T1 is 4 seconds in the simulation. We said T2 is 1 second or even put as 2 seconds. What does this mean? After the application of a 90-degree pulse, it would take the longitudinal magnetization, rather, I'm talking about transverse here. If you apply a 90-degree pulse, for the transverse magnetization to decay, it will take 6 seconds approximately. For the longitudinal magnetization to recover back close to its thermal equilibrium, we don't want to put 100% because it will never reach there. 99 is a very reasonable number. It's going to take 20 seconds. These are just example numbers I'm trying to give. So what you guys are able to realize is that the transverse magnetization almost always dies much faster than the longitudinal recovery to happen. So there is quite an amount of time that's present in the middle where we have to just wait, doing nothing. Slowly, you will understand that NMR is an insensitive technique, and therefore we have to do something called signal averaging. What is signal averaging? You got to repeat the same experiment and add the transients to get better signal to noise ratio. So the interesting aspect of NMR is that you can do something like that. But on top of it, what is going to happen? Yes, you can repeat the experiment, but you cannot repeat the experiment as fast as the signal dies. You have to wait for a much longer time before you can repeat that experiment. Just to give an idea in terms of the pulse program, slowly I'm introducing terms which we'll be using more and more. Let me try to draw. So this is the signal that you end up getting. So this is the RF pulse that is applied. Let's assume that we applied a 90-degree Y-phase pulse. What defines 90 degrees? Alpha equal to omega 1 times tau p. Correct? And omega 1 gets defined by B1, and the tau p takes care of making sure the alpha is 90 degrees. What's 90 degrees? The change in magnetization from its initial state to its final state. And the phase, the phi part in the equation comes up in the phase. Correct? You applied this pulse and you're acquiring a signal. We will understand the functional form of the signal in one moment, but this is a signal that you're acquiring. The signal will probably stay for about 6 seconds, assuming these time constants. These are quite typical for small molecules. Small molecules will have something like 2 and 1 here. I just took some numbers to give you an idea. Small molecules like ethanol, for instance. The signal can be acquired only for about 6 seconds. If you have to signal average, you have to apply the pulse again, get the signal again to add to the previous transient. And you can't do it right away. You at least have to wait 14 seconds in this example. There are tricks to avoid it, which we'll go later on. But this is an important aspect. Since NMR is insensitive, to improve signal to noise ratio, we have to do signal averaging, which is repeating the same experiment over and over again and keep adding the signal to it, and then processing it to get your information. Okay? All right, so this gives you some idea of what's going on. Let's go back to the math that we started with. We said dm over dt. I'll slowly drop the ROT because we have accepted the fact that we are in the rotating frame. This was the equation that we had, correct? So I'm going to write dm over dt is equal to, how does a cross product go? Ijk, mx, my, mz. Then you have bx, by, bz. This is a cross product, correct? And you guys might remember, we are already in the rotating frame. So bx component is going to be b1 of cos phi. I missed something important, huh? Nobody observed it. Yes, that should be a gamma. Of course, you can put the gamma outside this matrix also, but it would make sense to put gamma with b because it becomes omega. Correct? And what is the by component? It's going to be b1 sine phi. What is going to be bz? Delta b naught times k. The k is where you put already in the k part, right? Which is going to be equal to minus capital omega or small omega, where capital omega is the offset. Correct? So let's substitute these in the equation and let's see what we get. I mx gamma b1 cos phi. I request people to not just copy, please pay attention. All these are right outside the textbook, so you guys can find it rather easily. Check whether I'm writing the last part right. So it's going to be minus gamma or gamma times gamma. I think I've written it correctly, right? So the gamma will get cancelled. Please be aware that I might make some silly mistakes. I'm dropping the indices of rotating frame because we have accepted that we are going to be in the rotating frame to negate the effects of B0 based precession, right? So therefore, let's just take the x component of it, dmx over dt. That is going to be given by the product of this minus the product of this. That's how the cross product goes. It's going to be minus capital omega my minus gamma b1 sine phi mz. Correct? And what is going to be minus gamma b1 plus omega 1 sine phi mz. Everybody followed? And importantly, you guys knew from the Bloch equations what is going to be dmx over dt. That's going to be equal to minus R2 times mx. Makes sense? Everybody followed what's going on? What did we do? We are just decomposing each component of the magnetization to x, y, and z component. Similarly, what is going to be y? You're going to have these two, and you're going to multiply. There's a minus sign by itself. So it's, if I remember correctly, it's going to be plus omega times mx plus omega 1 cos phi times mz minus R2 my. Correct? I just did the same thing. I went a little fast. Why did the minus go away? Generally, the second one has a minus sign, minus j times. So I'm just putting the minus times minus becomes plus. Okay, and there is a, okay, so therefore this would be end up being a minus. That's why you should not do things in a hurry. Okay, right? And how did the minus R2 times my come? That's from the Bloch relaxation, ad hoc introduction. Right? Now the last part, dmz over dt is going to be, let's take these components out. It's going to be minus omega 1 sine phi with the mx plus omega 1 cos phi with the my minus R1 times m0 minus mz. This is the equation that we have. Correct? Therefore, all this can be put together with each other, which is d over dt of mx, my, and mz can be put together as a function of mx, my, mz. For this part, I'll not write the relaxation. We can always include this later. So what is this going to be? Minus R2 minus omega plus omega 1 sine phi. How did I write this? You want to take the product of this with this, minus R2 times mx is here, minus omega times my is here, plus omega 1 times sine phi times mz is here. Right? Similarly, oh, I said no relaxation, but I wrote it, but we will see. Then you will end up having plus omega. Thank you very much.
Minus R2.
Thank you.
Minus omega 1 cos phi.
Very good. Then here,
Minus omega 1 sin phi. Omega 1 cos phi. Minus R.
no.
And there's a
Minus R1, correct. Plus,
separate column plus R1 M naught 0 0.
that's correct. Is this right? No, check. I feel I'm doing something wrong. Okay, let me write it. So 0 0 1 is it? Minus R1 times M naught. No, this will just be M naught, right?
Yeah, R1 times M naught into 0 0.
Okay. That right? I think then this has to be a plus sign. Isn't it? Minus of a minus should become plus. Anyway, take a look at this. I've given you an idea how to generate this. Generally, when I'm talking and writing, I might make some silly mistakes. But overall, I hope you guys are able to understand the entire evolution of magnetization can be understood if you end up solving this matrix. And the point of this is that the rate of change comes up from wherever it is actually present. So basically, you can apply a 90-degree pulse and you can apply another 90-degree pulse. It's an accumulation of these things. The dt can be integrated over tau p for a pulse. Correct? So we can take a look at this equation for an application of a pulse. So let me copy this and we'll see whether we are right or wrong. So let's apply it for a pulse. Just for the sake of easiness, let's assume that relaxation does not occur during RF pulse. Why do we say this? We say this because tau p is in terms of microseconds. T1, T2 is in terms of seconds for small molecules. This time duration is so long, you can actually neglect relaxation during such a short duration of the pulse. Is that okay? So immediately what ends up happening? The diagonal goes to 0. We try to say when we apply the pulse, longitudinal or transverse relaxation does not have an effect. While you're applying the pulse, you're taking it away from equilibrium. If you're taking it away from equilibrium, the relaxation process should kick in. Yes, it does kick in, but the effect is so small because the pulse itself is so short. Let's ignore it just for the sake of it. Okay. Now, let's also add one more dimension to it. Let's assume that we are applying a 90-degree pulse along which phase you guys want. Let's apply along X phase. X phase means phi equal to 0. Correct? Phi equal to 0 means cos phi equal to 1. Sin phi equal to 0. Right? So therefore, what's going to happen? Sin phi components go away. And cos phi components become 1. Is that correct? Yeah? Let's add one more thing to it. What are we trying to do right now? How did the Bloch simulations work? The Bloch simulation works by solving this matrix. How is this matrix solved? Let's take it for a simple occasion so that you'll be able to understand how the math works out. That's all we are trying to do. So can we start from equilibrium? Just for sake of simplicity. So what is equilibrium? Mx equal to My equal to, very good. Mz equal to, very good. So plug it back in, you're going to get 0, 0, 1, right? So here you have a 3 by 3 matrix. Here you have a 3 by 1 matrix, which should result in a 3 by 1, right? Many are zeros. This time this will be 0. Is that right? But we have to be careful of the next part. So let's write dm d over dt of mx, my, mz is going to be equal to. Do we agree that the first row is going to be 0, 0, 0? Everybody follows? Very simple matrix multiplication. 0, 0, 0. Now the second one is going to be omega times 0, 0 times 0, minus 1, minus omega 1 times 1. It's going to be minus omega 1, right? Am I doing it correctly? Oh, sorry. There's a mistake here. I just said it's a 3 by 1 matrix. I wrote a 3 by 3. Please correct me. Sometimes it happens while I'm thinking and writing. Minus omega 1. Correct? The last part yet again is going to be 0 times 0, omega 1 times 0, 0 times 1. That's going to be a 0. Yeah. Slowly you guys are able to see this is the mx component. This is the my component. This is the mz component. Now you end up doing d over, instead of, you integrate it over the entire period of tau p. You are applying a pulse, right? You are allowed to integrate it from 0 to tau p. Is that true? Yeah. So I can always take things on the right side. Are you guys ready to accept x and y, z components are 0? Only y component exists. So I can literally write this as dm y is equal to minus omega 1 dt. Right? Then what did I say? Integrate over 0 to tau p. Right? 0 to tau p would also be integrate from 0 to tau p. We started with my being 0. Right? So when you end up integrating, you're going to end up getting what is my after the application of the pulse tau p for the duration tau p. This is going to be minus omega 1 times tau p, which is going to be equal to basically that's why it goes on the minus y. So you can always take the y to the minus side. Basically, it's a 90-degree flip, which will end up resulting in a minus y magnetization. I'm not saying minus y equal to 90 degrees. That's not what I'm trying to say. I'm just trying to give you an idea what is the effect of a 90-degree pulse and where do you end up coming. So let me not write this. You guys are able to realize that the right-hand side ends up, I can always take the minus sign to the left-hand side and make this plus. And omega 1 tau p is alpha. So basically, the effect of a 90-degree x pulse will be a magnetization along minus y. Repeat the same process for a 90-degree x phase pulse. Repeat the same process for a 90-degree minus x phase pulse. It'll go to plus y. Repeat the same process for a 90-degree minus y phase pulse. It'll go to minus x. Which is where the right-handed part comes in to see what how can you predict where the magnetization will be. Let me pause here for a moment and allow you guys to recollect your thoughts. What did we do? We just ended up redefining where we finished off last class. After integrating the Bloch equations with respect to relaxation, we end up getting this matrix. This is called the Bloch matrix. The Bloch matrix gives you the power to predict how does the magnetization change as a function of the effective magnetic field that is applied. Precession, basically. This helps you define precession. Correct? Slowly, you can always complicate your life and say, There are also offsets being present. You don't have to always start at equilibrium. Is that right? So let's do that experiment and simulation. Should we? Why should we always start at equilibrium? That's not fair. Maybe we want to start at non-equilibrium position at some point. So let's do that right now. Whenever you don't understand something, my request would be to go back to this Bloch simulation. There are better Bloch simulators than this, but the GUI and animation-wise is one of the best I've seen. That's why I'm showing this again and again. A more reasonable Bloch simulator would be in the Topspin software where you can see more. So let's go back to equilibrium. We can apply a 90-degree heart pulse. We went to the transverse. I can continue applying it. So how does the tau p come in? The tau p comes in depending upon where you stop. You can always stop wherever you want. You tune the tau p to get the flip angle. Correct? Similarly, if you end up having the XYZ axis properly given, you will realize that the flip is counterclockwise. So let's also do the same thing in slightly different fashion. Let's put a 30-degree heart pulse. What do you think will happen if I add another 30 degrees to it? Another 30 degrees to it. Another 30 degrees to it. Another 30. Yeah. Similar to applying multiple 90 degrees, you can also apply multiple 30 degrees. You can apply multiple alpha degrees. Nobody stops you from any flip angle. Phase matters, of course. So let's be a little careful here. Let's say we apply a 90-degree along X. If you continue to apply 90-degree along X, this will happen. On the other hand, I apply the 90 along X and then apply the 90 along Y, you see nothing happen. Because you're applying the rotation along the axis of the magnetization itself. M and B are collinear, no change happens. So please be a little careful with the phase. Did everybody follow what I'm trying to say? The flip angle has two components, the angle of flip itself and the phase at which it is applied. One can keep on applying it. And you now have the entire power over how to manage this. Okay? So far, so good. There's one more component that I would like to add here. We did see the relaxation part. I'll wantedly put a long T2. 9 seconds T1, 8 seconds T2 is not very realistic. But let's take an example so that you see the reduction of magnetization along the transverse plane as clearly. So look at the shadow. I'm going to apply the 90-degree pulse. You see that the shadow is slowly reducing. And why is it slowly reducing? It's an exponential decay, which you just saw a few moments earlier. mxy times e power minus r2 times t. Depending upon r2 and as the function of t, it's going to slowly reduce. And it'll go to 0 very, very slowly. Because it has already died and it's going to take infinite time to literally go to thermal equilibrium. Correct? This is what we wanted to see. Similarly, what you're also able to realize is the mz component. Now, forget what exists in the vector picture here. Look at the signal on the top right. I'm going to apply the 90-degree heart pulse. You'll slowly see the signal keeps decaying. Is that right? Why are the oscillations coming? Oscillations are coming because the magnetization is processing about B naught, which we have cut out in the rotating frame. So the oscillation that comes in induces an electric current. So that is the magnetic induction. The nuclear magnets that you have in your sample, which results in a magnetization, induces a current in the coil after the perturbation. Yeah. And this magnetization decays over time. Now, if you see the red signal, it's almost dead. You guys agree with that? So it has decayed. This signal is defined as the free induction decay. What is free about it? It freely processes about B naught after the pulse. What is induction about it? The magnetization that processes about B naught induces a current in the detector that you have. That is the induction. What is the decay in it? As a function of time, the transverse magnetization decays, and therefore this entire signal is called free induction decay, FID in short. I might end up using FID all the time from here on. And FID just means the signal that you end up acquiring after you have pulsed. Okay, we still do not know how the frequency comes up. You'll see that in a moment. Okay, that's the next part. I hope I'll be able to do justice to it. Did we understand how did we create bulk magnetization? How do you perturb it? How does it change as a function of time? That's what Bloch equations are all about. I hope you're able to visualize it. I hope you guys are able to even understand mathematically, quantitatively, how do things change. That is the entire purpose of the first 6 lectures and this lecture to tell you, okay, now we can predict what we want. Followed? Yes? Let's do one more simulation before we go to the signal part of it. That's an important simulation again. Reset. The important part of that simulation is, let's go to equilibrium. We saw how the 90-degree pulse starts to get things back up. Okay, I'll put 5 seconds and 3 seconds. Okay, now let's also look at how does a 180-degree pulse behave. Ended up doing a 180-degree pulse. More or less, you guys realize there is literally no transverse magnetization that comes up. Did I apply a soft pulse or a hard pulse? Did you realize almost no shadow came up? So please be very careful about it. Why am I trying to do this? If you're able to achieve a perfect 180-degree pulse, there is no transverse magnetization. There's no transverse magnetization. That means you detect no signal. Why you don't detect any signal? Because the magnetization is still 180 degrees from B0, so no precession comes up. If you paid a little bit of careful attention, something comes up. Okay, don't ask what it is right now. We will avoid this for the current time being, but you can assume for all practical purposes, it's actually 0. And the recovery only happens along the z-axis. So if you apply a 180-degree pulse, turn the receiver on, you get no signal. You apply anything apart from a 0-degree, 360-degree, or a multiple of 180-degree pulse, you will get some signal. Followed? I don't know whether they have a 135-degree pulse. They don't have in this one. Maybe I can try the 160-degree pulse. Look at the same thing, 160-degree pulse. In this case, you see more of the red coming up, which is the transverse magnetization. Anything that's not a 0 or an 80, 180 or any multiples of it, you will see transverse magnetization. You will collect a signal. But most importantly, if you apply a 180-degree pulse, the recovery is such that it will only go through population difference. No coherence is generated. Very, very important aspect. Many people try to imagine 180 degrees. Oh, it slowly comes back up. No, that's not the way it comes up. It actually grows this way. So be very careful about it. Your 90-degree comes this way and the magnetization slowly comes back up this way. That's not the way 180. 180, don't imagine it's going to come this way. It does not come out that way. These are the very important deductions that we end up getting from whatever we have generated this far. Okay. Since it's just 3 minutes away, let me pause and ask if there are any questions in what we have studied so far.
Use the word transient when you are trying to use it. What do you mean by transient?
Generally, I don't introduce this until later, but I wanted to emphasize this towards pulse programs. What's a transient? Every time you collect a signal, we call it. So you want to measure it over and over. That makes it a multiple transient experiment. So you add those to get the signal average. Do not worry about it. We'll come to it later. But the long and short, you see the signal dies faster. You have to wait a significant amount of time. Repeat the experiment. Make sense? So for biomolecules like proteins and nucleic acids, the T2 times are in the order of 50 to 100 milliseconds, while T1 is in the order of 1 to 2 seconds. Slowly, you guys start to realize it will die very fast. Within 150 milliseconds, it will die. But for recovery, I had to wait about 3 to 5 seconds. So most of the NMR experiment, the pulse is very short. The acquisition is, let's say, 200 milliseconds at best for one-day experiments. Your wait time will be 1 to 2 seconds at least. About 95% of the NMR experiment is where the spectrometer stands idle. We can't do anything because it has to come back to some steady state so that you can repeat it. The example of this is where I give you breaks after every class. If I end up doing 3 hours of NMR lecture in one shot, it'll be gone, right? This itself, you guys are going to the edge of understanding, not understanding, and then coming back every class, right? You have to go read, think, understand, and then come back. Similarly, NMR spins also work the same way. You got to let them relax and come back. Was that a question?
How many iterations do you normally use?
That depends on the signal to noise. Those are very good questions. Let's go to them when you are. Remember, I defined something called signal to noise ratio should be minimum 3:1. If you have less sample, you may not be able to get 3:1. So you go on until you get 3:1, for instance. Generally, people like 10:1. 3:1 is still borderline. Every experiment comes with something called artifacts, which are mistakes, which shouldn't come, but they are coming. I told NMR is very sensitive. So if you end up running FM radio on the side, that might get picked up. So, or a lift that keeps periodically going up and down, a lorry that keeps going across the road. So that's why people are very cautious about keeping NMR in a certain place. The problem is the lorry won't go the entire day all the time. It would have gone when you ran the experiment. You would have gotten a peak and you won't understand why it hit the peak. Come, you would interpret this as a impurity maybe, or some other state that the chemical switch is trying to make you understand. So it's a very sensitive technique that way. Luckily, signal averaging helps. Let's say you're running the experiment for 1 hour and the lorry went for 5 seconds. That won't affect. But on the other hand, the lift right next to the NMR keeps going up and down aperiodically. NMR works on periodicity. The oscillation is what is going to give you the signal, which I was hoping I'll teach today, but I couldn't get there. You end up doing something called a Fourier transformation to get your information in the frequency domain. Remember, you've gotten the information in the time domain. You acquired signal as a function of time. Time and frequency are inversely related. And therefore, you'll be able to extract the frequency information from the time domain signal. To finish off, to make you guys understand why this is great and important, is that generally spectroscopy is done by sweeping across energies to match and get an absorption spectrum. You can imagine this as an example, classic example given for NMR from NMR textbooks. You take a piano and there are a given number of keys. Let's assume that your ears are very good in picking up frequency. What would you do? Press first button, listen, write the frequency. Press second button, write the frequency, and you go one by one. Correct? NMR is this wonderful technique where you hit all the buttons together, record the signal in one time. Literally, all 30 keys at the same time, jam it, record the signal. You have this magic box called Fourier transformation, which will give you separate frequencies. Now you'll ask, so what is the advantage? Instead of hitting 30 keys one after the other, 30 units of time, you got it in 1 unit of time. And most importantly, be it continuous wave mode of scanning the frequencies or pulse technique, the information content is one and the same. The sensitivity problem is one and the same. Now, if you want to repeat for signal averaging, you realize that the pulse technique is better because you can hit it once, keep on repeating it to get better signal averaging. And it's much faster. So for single scan experiment, it doesn't make a huge difference between continuous wave or pulsed NMR. But for multiple transients, pulsed NMR techniques are far better. We will never discuss continuous wave NMR in this course because it's literally 50 years away and nobody does continuous wave NMR anymore. They do continuous wave EPR, but NMR is all in the pulsed mode. I hope now I have given you an idea what gives signal from NMR. How does the signal give us information? Is next class, tomorrow's class. Thank you very much.